Graphs of polynomials. By now you should have a solid grasp on graphing degree 1 and degree 2 polynomials. What we're going to be doing in this video is graphing degree 3 and degree 4 polynomials. Those would be your cubic and your quartic polynomials. What we learned from graphing these two degrees will extend on to higher degrees like 5th degree, 6th degree, 7th, 8th, and so on. Basically, the odd degrees all sort of act the same way, and the even degrees all sort of act the same way as well. A polynomial in general can take on this structure, which when you take a quick glance at that looks super complicated, but this is a polynomial of degree n. That means that the highest degree is n. And literally all you have in standard form are a bunch of terms where the x's are raised to different powers, they have their own coefficients, and then we tend to write them so that the exponents are decreasing. Okay, so at the very front, this first term here, that would be x to the nth power. Okay, so that would be your n degree polynomial. You have a coefficient in front of it, which is called an. That just refers to a specific coefficient that goes with that term. Then after that, you're going to have x to the n minus 1 power. Okay, that would be 1 degree less than the previous. For example, if this was x to the 5th power, this would be x to the 4th power. In front of that, you've got a coefficient a n minus 1. That would just be a specific coefficient that goes with that term. And it continues down the line, okay, it continues down the line. You'd have your quadratic term with its coefficient, you'd have your linear term with its coefficient, and then you would have a constant. For example 1, we're going to start with a monomial. A real simple one here, y equals x to the 3rd power. Okay, and this is a graph of y equals x to the 3rd power. Okay, so it has this weird little curve shape over at the origin. Other than that, it kind of looks like your quadratic, right? It sort of looks like you have a parabola here. This could be a parabola on the downside, except that it does go in that down direction. Okay, so let's just identify a few points that we see here. If you were to plug in a 0, 0 cubed is 0, so you get the origin. If you were to plug in a 1, 1 cubed is 1, so you get a point here. Okay, then beyond that, the numbers start to jump quite a bit. Okay, if you plug in a 2, 2 cubed is going to be 8. Your next point is going to be up here. All right, on the other end, negative 1 cubed is going to maintain that negative, so you get back negative 1. Okay, so those are a few standard points that we could look at for y equals x cubed. All right, what we want to do next is transform it. Move it around, stretch, compress, possibly flip it. So for any degree power monomial, you could relate this to what we learned about quadratics. Okay, so here's a typical equation that you could be asked to graph with basic transformations. The plus 3 that we have on the inside is going to be a horizontal shift. Because it is a plus 3, it is going to move in the opposite direction, which means that it's going to go to the left 3. Okay? The plus 3 that we have at the end of it is going to tell us that the graph is going to move up. It's going to move up 3 units. Okay, the way that I would graph this is to use the point of symmetry that we got in the graph, which is here. Take that point and shift it left 3 and up 3, which is going to put it here. Okay, now if we didn't have anything else, if we didn't have that 1/2, what I could do is just plot a point here, then I could go over and up another 7 to plot a point. Of course, that doesn't fit on my graph here. The other direction, I could go back 1, down 1. After that, I could go back 1 and then down 7 for that point. The 1/2 is going to be a vertical compression. Okay, so whatever you think the outputs would be, they're going to be half as much from that point that we've just plotted. Okay, so instead of going over 1 and up 1, we're going to go over 1 and up 1/2. You get a point right here. And instead of going over 2 and up 8, what we're going to do is go over 2 and up 4. The other side is going to look the same, just in the down direction. We'd go over 1, down 1/2. We could also go over 2, down 4. And that's it. When a degree 3 or degree 4 polynomial become the sum of monomials, okay? When they become the sum of monomials, the shape of the graph can significantly change. It takes on a completely different image. Okay, here's our x cubed function, which we just talked about and graphed. If you change it by adding more terms onto it and other things like factors, you get a completely different picture. Okay, so we still have the x cubed as a leading term. It does have a coefficient of a 2. We also have added on, this is the most important part here, we've also added on a negative x. Okay, we're subtracting x from it, and it changes the image. The bend that we have in the middle is now going to go up past the x-axis, come back through the origin, dip underneath the x-axis, and then come up. It takes on that shape. It gets these extra little bends that would be in there. The third picture is not a lot different than this one. What I want to highlight in that one, though, is the leading coefficient is now negative. When that becomes negative, the graph is going to flip vertically. So we see the graph coming down past the x-axis, curves back into the origin, comes back around. Okay, and as just a note here, not all these graphs are actually going to pass through the origin. These just happen to be the samples that I used because they seem to relate best to the original parent function. Okay, but as you add these extra terms in there, we could add quadratic terms, we could add linear. Constants aren't going to change much, that's just a vertical shift. But if we add the quadratic or the linear terms, you're going to start to get these little bends in the graph. All right, the first takeaway that I want to get from the graphs is going to be end behavior, the end behavior of these. This can come in really handy when you're trying to sketch a graph. But first, let me make the statement. We say that the graph of a degree 3 polynomial is an S shape. Okay, that sort of wiggle that we have in there, we're going to describe it as an S shape. Of course, it doesn't look exactly like an S, but it's got that extra kind of bend in the middle of it, so that's where that's coming from. If the leading coefficient is positive, such as x cubed, that would just be a positive 1, or 2x cubed with a positive 2, but not this. If the leading coefficient is positive, the limit as x goes to infinity, as the graph goes to the right of f of x is going to be infinity. As these graphs go to the right, they continue to move up forever. On the other end, as x approaches negative infinity, as we go to the left forever, the graph is going to head down, which is going to be negative infinity. If the leading coefficient is negative, like the last example here, that changes. As x goes to the right forever, the graph is not increasing. It increases a little bit here at the beginning, but overall when x gets really large, as we go to infinity, way out to the right, the graph is going to continue down. We're going to get negative infinity. And as the graph moves to the left, we get positive infinity. That's pretty good. For example 3, we're going to sketch a graph of a quartic polynomial. That would be degree 4 polynomial. Okay, now we don't really know how to graph these for real yet, so what I'm going to do is just graph it in the calculator and do a quick sketch of what it looks like. Okay, now one thing I want to note, because it might be a little bit hard to see here, is the scaling that I did for my graph. This is a 4, okay, that is a negative 4. So my x's are going to range from negative 4 to 4, but my y values, I've got 40 to negative 40. Okay, so the graph that we're going to be looking at is very compressed. Vertically, it is very compressed. All right, so here's the equation typed into the calculator. Okay, beyond just hitting graph, what I'm going to do is go to the window and show you that I set the window to fit the same graph that I have behind this. Okay, I have an x minimum of negative 4, x max of 4. The y minimum, negative 40, max 40. Okay, so then when I hit graph, it's going to best fit what I have here, which is going to look like that. The graph appears to start way up here. Okay, that's negative 4, so before that, it's going to come down, seem to pass at negative 3. We don't know that for sure, but we'll go ahead and assume it's about negative 3. It will then turn, come back up through what would be maybe negative 2, hit a high point short of the y-axis, come back around, looks like at 1, big dip, comes back at 3, then continues on up. Okay, so it appears to make contact about here and here. Somewhere up here, we got at 1, we got at 3. Okay, so the graph is coming from the top, little dip here, oh, high point is not going to be there. The high point is going to be a little bit before it, maybe here. So let's aim for that. All right, we're going to get a big dip here, goes beyond 40, and comes back up. Sort of has that shape. Not a perfect picture, but I think we get the idea. Overall, oh, and I added a little arrow here because it's going to keep moving in that direction, which is the same thing as over there. All right, overall, here's what I want you to take away from this. When we've got all these terms in here, this is the general shape that you can get. If the leading coefficient is positive, which is what we have here, we have a positive 2 there, the shape of the graph is going to look sort of like a W. If the leading coefficient is negative, we should expect the whole thing to flip over, which is going to give you an M shape. Creating a perfect graph of a higher degree polynomial by hand is near impossible. However, a basic sketch of the graph is possible. The thing that we're not really going to be able to figure out are going to be the maximums and the minimums, like how far the graph actually stretches in those directions. Okay, what we're going to base our information on is going to be the end behavior and zeros. All right, for example, 4, what we have is a cubic polynomial. It is a cubic polynomial. It's going to have that S shape, but it is presented in factored form. Okay, so from factored form, what you can gain will be all the zeros, the x-intercepts. In this case, that would be at -1, +1, and +2. Okay, so as far as my graph, let this be the x-axis, let that be the y-axis. Okay, so I'm going to have intercepts at -1, at +1, and +2. Being that we have a cubic function, it's going to have an S shape. So there's two things that it can do. The graph can either start from the bottom, go up through this point, turn around, pass through that point, then make one more turn through that point. Or the graph could start from the top and do the opposite. It goes through here, comes back up through that point, back down through that point. And we can determine that based off of the leading coefficient. See, if all this was multiplied together, the leading term would be created using this x, and this x. That's the x cubed, which will ultimately end up being just x cubed. Okay, we don't have any other factors that are out front. So the leading term is going to be x cubed. But more importantly, it's going to be positive x cubed, which means that the graph is mostly moving up. It's going to start low. It's going to go up, come back around through that point. You're going to need a little dip so that you can go back through there. All right, so what we don't know is the height of the peak and the depth of that valley. But generally speaking, this is the shape of the graph. It has intercepts at these spots, and it seems to be mostly moving up. You just have that intermediate part where it kind of wiggles and then heads back in the up direction. Example 5. Let's go ahead and try this with a quartic function, Okay, what we do have here is a standard form quartic. We don't have it in factored form. What we would get from the factored form would be all of the zeros. So what we need to do first is actually factor this. Okay, now factoring higher degree polynomials tends to be a difficult thing. Okay, so what we're going to start with is one of the zeros. You are going to be told that you do have a 0 at 1. You do have a 0 at 1. So that would mean that you would have a factor of x minus 1. That would be a factor. So I'm going to use synthetic division to remove that factor. Okay, I'm going to start up my synthetic division with the box. In the box is going to go the 0, which will be a positive 1, the opposite of that number. Next to that, we're going to write our coefficients. We're going to check our degree. So degree 4, we should have 5 terms. But we've got 1, 2, 3, 4. What we're missing here is the constant at the very end of this. We're missing the constant. And that should tell us something important here. That from the very beginning, if we wanted to, we could factor an x from each of these. which would represent a 0 at 0. Okay, but we'll let it be for right now. All right, coefficients, you got a 1, you got -1, -4, and 4. And the constant, which is the 0. We'll drop the 1. 1 times 1 is 1. That'll give you 0. That would also be 0. So we get -4 times 1 is -4, which will give you 0. 0 times 1 is 0. And right here, that is the verification that this is, in fact, a root. Okay, so what do we have left over now? This is going to represent an x cubed. That would represent an x squared. This would represent just a regular x. Okay, so we would have that. In front, we've got this factor. Okay, now I want to continue to factor, oh, there's an x there. All right, what I want to do is continue to factor this part here. Remember, from the very beginning, there's an x in all the terms. So that's still present here. We can factor that x out. We'll go ahead and move it all the way to the front. That leaves you with x squared minus 4, which happens to be the difference of squares. So from there we learn we've got zeros at 0, at 1, at -2, and +2. So we'll plot those points. All right, and being that this is a quartic, it's either going to have a W or M shape to it. Because the leading coefficient is positive, it's going to have that W shape. It opens up. The positive tells you that it opens up. Okay, so just a quick sketch. And the graph is generally going to look like that. What I don't know is how far this goes down. So even though this is at -2 on the x-axis, and that is a 0 and a 1 and a 2, this is most likely not a 1. Okay, I do not know the scaling appropriately for the y's here. And last, I want to bring up double and triple roots. You could also refer to these as double and triple zeros. If you have a factor, meaning that you're looking at the polynomial in factored form, that's present 2 times or 3 times, you get some special cases here within the graph. Okay, so if I had x minus 3 squared, that counts twice in the factored form. It is x minus 3 times x minus 3. For example, here, we've got x minus 3 to the second power. This is a quartic function. It has a positive leading coefficient of 1, so it's opening up. It has that W shape. When we see it in factored form, it looks like we just have 3 factors, but this one counts twice. Okay, you got x minus 3 to the second power. So at that 0, at 3, you're going to get a unique thing here. You get tangency. The graph, as it dips below over here, when it comes up at 3, it doesn't pass through the 3, but it just bounces against it. It runs tangent, comes back around to go through that last root. Okay, double roots are going to create this kind of bouncing look that you have. A triple root, such as over here, x minus 2 cubed, is going to look like it's about to bounce against it. It's going to turn into it like it's going to bounce against it and go the other direction, just like the double. But instead, when it hits that spot, it's going to switch directions and move down. Okay, and you should recognize that shape from the parent function of cubics, y equals x cubed. Okay, so it still has that same kind of weird wiggle in the middle there. But that's what you get when you have a triple root.
Wait,